right, back in business. All right, so moles of benzene. Should come out to like 1.28 moles. Good. So then the mole fraction of benzene yes. Okay, I see a few people nodding. Good. So now we're ready to plug it in. So we have 0.865 times the old vapor pressure of 400. And that should come out to 346. Right, so pure benzene has a vapor pressure of 400. We now have less than pure benzene, so we have a lower vapor pressure. Everybody follow what I did so far? Just like we did last Friday, just plugged it in. Yeah.
Can that only be in milligrams of mercury, or can it be in any?
It can be in any pressure unit. Yep. It's just some fraction of the original pressure. So it could be in atmospheres or something else. All right, so maybe thinking, well, okay, it's a lower vapor pressure, but I thought you just said it was boiling point elevation, right? How can you have low? It's because, let's look at a graph. If you don't know this about me, I'm passionate about graphs. I really, really love graphs. So we do a lot of graphing in here. A lot of graphing in here. All right, so let's see if I can get that all to work. Focus. There we go. All right, so here was our boiling point of pure benzene. It's about 80. And at regular atmospheric pressure, right, 760, we would expect, right, that's where it boils. Well, now, we now have, this is our benzene and solute curve, right? It's shifted to the right. Boiling point of the solution. In order for us to hit that same 760 spot, the boiling point had to elevate. It went from 80 to, I think that's like 85. So the curve has shifted. And so at the same atmospheric pressure, it used to boil at 80, but now it has something else in it. So for it to boil at the same atmospheric pressure, you have to apply more heat. So the vapor pressure went down, but the heat required, you can see vapor pressure right here. It decreased, and that decrease pushes that whole curve to the right. You might have to ponder on that for a little bit.
Vapor pressure went down, boiling point goes up.
Yes, that'd be a good relationship.
So regardless of what you add, it's going to increase the boiling point from the
Yep.
stuff you add in the solution?
And so the benzene plus solute, is that leading to the vapor pressure going down?
Yes.
Is that what that is?
Yep. So this was our original pure benzene point. When we added something to it, the vapor pressure went down. And that down actually pushes all the points to the right. Moves this whole curve over. So we can actually come up with a equation, which for lab this week, this is what you're looking at, right? This is the boiling point elevation. It's the same equation for freezing point depression. So the change in temperature of the boiling point, which is this, is equal to this K, which is the molal boiling point elevation, which has units of degrees Celsius per mole. More for molality, sorry. Times the molality of the solution. So you can see those molalities will cancel out. All right, this is degrees Celsius per molality times the molality times this crazy thing, I. Not like math I. There's a different I. This stands for best way to explain it. It's related to the number of ions in solution. Yep. Yeah, I have a practice problem about that here in a second. But yeah, it's the same I. It's if your compound doesn't break up. Oh, question first.
For the M, is, oh there, this is M of the solute and the molarity of solution.
Oh,
The solution. Is this to be the solute?
yeah, make this one solution. Yeah, the molality of your solution.
Is K going to be given to us?
It is. It has to be given. Or it's in the table. It's a constant. And an I you can figure out. So I is the number of ions. So, right, if you have something that doesn't break up, the I is going to be 1. You have, so like in the hint, you have sodium chloride, and so the hint, when the question was phrased differently, was telling you that the I was going to be 2, right? Because you have 2 sodium chloride breaks up into sodiums and chlorides. So we'll do this practice problem. Maybe that'll help out. So the melting point of water, pure water, right, is 0 at 1 atmosphere. We have now added 12.15 grams of zinc sulfate to 161.2 grams of water. So 2 parts. 1, we'll figure out the molality. And 2, we'll use that molality to figure out the new melting point. So looking at the molality, what do I need to get? What's the units of molality? Right, moles of solute, yeah, over kilograms solvent. So this is really part A. We need to figure out moles of zinc sulfate. And that should be pretty straightforward. I gave you the molar mass and the grams. So go ahead and take a second, figure that out while I get my calculator out. All right, so then we figured out moles of solute. I know that this is 161.2 grams of water. What do you know about pure water that can help us turn grams into a mass? Grams is a mass, so do I have to do anything to it? I need to convert to kilograms, so I shouldn't have to do anything crazy to it. I just need to make sure I'm in kilograms. It is tempting to change all kinds of things in all kinds of other units. So a lot of this semester is just going to be careful reading, making sure you know what you're trying to get to and what units they already gave you. All right, so then to figure out the molality, I haven't messed up so far. So far, so good. Okay. So now we're ready to plug this into our new equation to figure out the new melting point. So, the K will be given to you in the table, and it happens to be for zinc sulfate. The K is negative 1.86 degrees Celsius per molality. We just figured out the molality. Then the last part is figuring out this letter I. So I had zinc sulfate. Is zinc sulfate ionic? Yes. So if it's ionic, we know it has to break up. How many different ions does it break up into? 2. Just 2. Zinc sulfate. All right. And if you don't remember your complex ions, you can go back to chapter 2. Check those out again. Remember which ones stay together as complex ions. So then, let's calculate that out. Negative 1.86. Are we done? If I'm asking a question, the answer is probably no. All right, so that's the change in temperature, right? Water normally melts at 0. And if this is a change, it's telling me I have to do what to figure out my new melting point or boiling point. It happens to be I picked a temperature where the answer is the same, only because water is 0. But that is what you do next. This is really a freezing point depression question. I realized it's in the wrong section. This is a freeze because where I'm looking at melting, and melting and freezing go together. So, relabel this question. Realize I have a bad question in the wrong section. Question. Now I've confused everybody.
So you add the new boiling, the new freezing point to the original one?
Yes. Yep. So freezing point depression, it used to freeze at 0, and now it's going to freeze at negative 1.74. There's a better freezing point depression question. But it's the same equation for both. So instead, VP-B, freezing point. Make a note in my notes. That's in the wrong section. Have I confused anybody else in any other kind of way? Just general confusion? Well, don't you worry. You're going to do this a whole bunch today in lab. You are going to figure out the freezing point of just plain water. Then you're going to add a salt and figure out its new freezing point. Surprise, spoilers, it's going to be lower. If you don't get it to be lower, you've done the experiment wrong. So, good. All right. In that case, let's go on to osmosis, because since we did both freezing and boiling kind of all at once. All right, so the last colligative property is osmosis. And osmosis is the movement of solvent molecules from a region of lower concentration to a region of higher concentration. Mm-hmm.
So is this line before this, the freezing point expression?
It's the exact same equation.
Okay.
It's the same equation. And you can think about this, you now know the answer to this. Hopefully everyone has antifreeze in their car today. All right, because if your car ran on just pure water, your car would have not started today because the water would have all frozen. So if you add the antifreeze, the freezing point lowers so it can get colder outside before your engine seizes. Same thing with windshield washer fluid. You add some sort of salt to it so that the windshield wiper fluid doesn't freeze. There's your fun fact conversation starter for later this week. All right, so osmosis, we're going to flow from low to high. So here's a picture that may be more helpful. So here's my pure water on the outside of my balloon. And inside my balloon, I have 5% sugar and 95% water. So does inside or outside the balloon have a high concentration of sugar? Right? So this is my high concentration. This is my low concentration. So the water is going to flow from low to high. So it's going to make my balloon fill up with water. And the reason for that, it wants to get both concentrations the same, right? So this has very little, this has a lot. So it's going to dilute it by adding more water inside the bag so that the relative concentration goes down inside the bag. Maybe thinking, when do I ever run into this? Well, the most common this is going to be the most common way you're going to run into it, IV saline drips, right? In your body, you have known salt concentration, right? Your body has some percentage of electrolytes if you're all trendy and drinking your Gatorade and whatever else. So your body has some sort of salt concentration. Right? So if you need an IV, you're going to want the same salt concentration that they're pumping into you that your body already has. Right? Because, imagine this is your cell, and they pump in the wrong concentration of salt. They put in too low concentration. Well, now your cells are going to super swell, possibly explode. That's not good. That's actually going to make you feel much worse than you were already feeling. What if they do it the opposite way and put in a gigantic concentration of salt compared to your cell? It's going to shrink up, right, and become too small. And so those nurses and doctors who are figuring out your IV saline drip better have the right concentration compared to your cells in your body. Otherwise, you're going to be in much, much worse shape off than you were when you began. All right, that's everything I have about colligative properties. Hopefully, you're not too baffled by that. But let's get started in the next few minutes here, talking about my favorite chapter, absolute favorite chapter, which I tell my students this all the time in 109, and they don't believe me. This is the one chapter you're going to use in every other science class you take. You're going to need it for biochem, you're going to need it for pchem, you're going to need it for biology, you're going to need it for animal science, kinetics. This is the chapter that I assume a lot of knowledge on your part if you take my biochem class, because I know you've seen it, and I've definitely taught it to you. And so kinetics, super critical for all other areas of science. So kinetics is just a measure of the rate of a reaction. So the investigation of the rate at which reactions occur. And so you're thinking, rate, how does that apply in chemistry? It's the same as in physics or anything else. How fast something's changing over some period of time. And we're specifically going to be looking at reaction rates. Which is how fast a reactant is consumed, or how fast a product is formed. And this is something we're super interested in. You need to know, is this going to be a fast reaction? Is it a slow reaction? How much reactant do I need to put in there to make the final product? If I heat it up, how will that change it? If I cooled off, how will that change it? The reaction rates are critical for all of our, especially for your body. Everything in your body requires how fast or how slow something's going to be made or used up. So we'll do some big review about some very standard terms, right? So here's my rate again. Rate is a change in quantity divided by some sort of time. So I could write that mathematically, right? Change in x, where x is whatever I'm measuring, over change in time, delta t. Which, if you want to be more specific, right, it's final minus initial. Right, that's what change in is, delta t, delta x. Whatever concentration maybe you end up with minus how much you started with. Final time minus initial time will give you how long it took. So we talk about rates all the time. You probably just don't think about it. Right? A car drives at a given rate. Change in miles over change in hours. Talk about miles per hour. We talk about meters per second for the speed of light, like how far did the light travel over what distance of time. In a chemical reaction, we are specifically going to be looking at concentrations. Over a given time. So we're going to be looking at, this is typically going to be molarity, big M. How the change of molarity changed over a given time period. So you know I'm passionate about graphs. There's a heavy graph chapter. So this is out of your textbook, so don't feel like you have to sketch the whole thing out, but we're going to look at some important points of our little graph. All right. There's a lot of information on here, so let's first look at what I am graphing. So I am looking at, this is a graph of change in N2O5 concentration over some change in time. So on the y-axis, I graphed concentrations. That is concentrations of N2O5. And on the x-axis, I graphed time. Right, I put time on the x-axis because that's independent. Time's going to march on regardless of what you're doing in the reaction. So this guy always has to be the independent variable. This is the dependent. We're going to just about always put time on the X, concentration on the Y. All right, so ignore all the stuff over in the boxes here for just a second. I took my data at 1, 2, 3, like 7 or 8 points, right? And I started off with the reaction. I had 1.105 concentration at 1 hour. At 2 hours, I now have 0.8. At 3 hours, I have 0.55, right? So the concentration of my reactant is decreasing as time goes on. What is happening to my concentration of product? It should be increasing, right? For those supply and demand curves, it's kind of the same thing. As this decreases, you could imagine a curve that's going equal and opposite in the other way, right? Because as this is decreasing, your product has to be increasing. Something like this. Right? At time 0, you have all reactant, 0 product. As time goes on, you lose reactant and you gain product. And at some time way out here, you have no more reactant and all product. Yeah? Okay. So, we can measure how fast we are losing reactant or gaining product. We can measure that. And so for this, the average rate is going to be how much you lost from here to here, right? That change in X, or change in Y, change in concentration, over a change in X, which is time. Delta Y over delta X. Change in concentration over change in time will give you an average over that little time period. So average rate is looking at small time periods. This is just the intro. We're going to spend a lot more time talking about average versus instantaneous. Where if we look at the instantaneous rate, we are looking at a single point. Instantaneous looks at one and only one concentration. So in this case, they put 0.034 as their concentration. And what they're going to do is they're going to look at 2 points around it. They're going to look at this point, this point. You guys did tangent lines back in wherever you guys did geometry. It's all right, we'll do them again. The tangent, right, is the point that goes through those 3 points, not necessarily the curve. So it's near it, but not on it. And so they're picking this point and then doing the same calculation to figure out what is the instantaneous rate at that one point.
So the average rate is like a sample?
Mm-hmm. Yes. Yep. So average, as the name implies, is over a block of time. Not a huge, not the whole graph, but it'll be a small chunk. Instantaneous, you want 1 point. But obviously you can't figure out the rate at a single point. So you look to points either side of it and do the calculation. You do. You randomly pick 2 points on either side. I mean, not totally random. Like I wouldn't pick points that weren't on the curve, but how far away is up to you. All right, so let's, now that that's some intro, let's do some actual walking through of rates. So here's my reaction. I got nitrogen dioxide breaking down to nitric oxide and oxygen. That's it.
long do we get at the end of the class to take the quiz?
We get 10 minutes. So I'm going to do this slide, and then you get the rest of the time to do the quiz. So I keep looking at the time. Make sure you get 10 minutes. It's 4 multiple choice questions and like 1 short answer, so it shouldn't be too bad. All right, so let's say I have this reaction. Now we'll do appearance first. We'll do appearance. We actually want to know all 3, so we'll put that together. So we want to write an equation that relates the appearance of NO, the disappearance of NO2, and then the appearance of O2. We want to know how they're related. So we'll go left to right. We'll look at this guy over here first. All right, so NO2 is disappearing, right? Because it's a reactant, it's becoming a product, so you should have less over time. Bless you. So we're going to look for something like that, right? Change in concentration over change in time. Now, let me ask a question about this. Can you have a negative rate? No, right? If you're thinking about miles per hour, if you put your car in reverse and drive really fast, is that a negative rate? No, right? It's a positive rate going in the negative direction. Right? So I can drive 60 miles per hour backwards or 60 miles per hour forwards. Probably wouldn't want to drive 60 miles per hour backwards. Seems kind of a bad idea. So if this is my rate equation, and I'm looking at something disappearing, I can't have a negative rate, so how do I unnegative a negative? Add another negative. So rates of disappearances are negative top over bottom. Right, because that way I get a positive number at the end. All right, we'll stop there, so I make sure you guys have enough time for this first quiz. Make sure I'm not rushing you.